Okay, welcome everyone. I'm Owen O'Malley. This is Alan Gates. We're going to be talking today about adding ACID to Hive. We're both co-founders of HordeWorks and have both been involved in various parts of Hadoop for a very long time. You can obviously get our email and Twitter handles off of there. So what's the problem we're trying to address? Currently, you can update your data in Hive, but the granularity of those updates has to be at the level of a partition. You can insert overwrite a partition and it'll work great. You can create new partitions, that works. But you do everything at the level of the partition. And that means that for many people, they end up with daily, hourly, or shoot, I've even seen partitions down at the 5-minute level. And that means that you end up with a huge number of partitions in your table that you don't actually care about. And they cause performance problems as you're going along. I don't know if you've ever tried this. I've actually seen this done. I've seen a customer delete a table, just do drop table with 2 million partitions. Any guesses how long that takes? Under Hive 12. Actually, Hive 11. It takes days. The HDFS delete finishes instantly, and the talking to the metastore takes days. Not good. The other issue with doing the updates is if you're doing an insert overwrite and someone's reading the data, there's a chance they'll see that directory in the metastore and we'll start reading the data, and the files aren't finished yet. So they'll get bad data, they'll get incomplete data, they may fail if the file's incomplete, and so they're going to die. That's not okay. There is a Zookeeper lock manager, but I haven't talked to anyone who's used it in production and been happy with the results. So I would avoid that if I were you. And finally, one of the things that we've been doing in Hive is trying to make the SQL closer to the standard. Right? I don't like to say we're going towards ANSI SQL, but we want to make the experience for users as close as we can to the normal SQL, and there's currently no delete, update, you can't insert a couple values, none of that works, and it makes ad hoc work very difficult. Do you like my slide? So, do you guys know what ACID is? Who knows what ACID it means? Okay, not that kind of acid, but. So ACID is the database property that lets you get atomicity, concurrency.
Consistency.
Consistency, thank you, sorry. I'm screwing it up. Apparently I had too much acid. Isolation and durability. And Hadoop has traditionally done without ACID, and they've claimed that it's because it's a trade-off for performance. But your data isn't static, right? You don't load up your data into Hadoop and then just leave it there and run queries on it. You actually want your data to change as the underlying data changes. And it's changing hourly, daily, even faster. So it is possible to put in ad hoc solutions into Hive. You can use input formats and play all kinds of games. But it's a lot of work, and you really would rather not do that. And so we're baking this stuff into Hive so that you can get ACID out of Hive natively. Obviously, you want exactly consistent views of your changing data. I like to quote Yoda when we talk about making changes here. Do or do not do. No try. Don't try. Okay, so what are the use cases we're going after? We're not trying to hit the world's use cases, but these are the use cases that are important. First is updating a dimension table, right? If you've got a list of customer addresses, you want to be able to update your customers without blowing away any queries that are in the process of being run. That's just a good feature. You want to be able to delete old records. If your customer doesn't want to be in your database, you may have an actual obligation to remove them completely out of your system. And so you want to be able to delete old records. Another use case is if there's a fact table, you may actually need to go back and restate data. Currently, that's a pain in the tail. You have to rewrite those partitions and go and hope you don't have any queries running. And we want to make that possible. I've got a customer that actually is running something like this in production, and they've got an ingest rate of 3 terabytes a day, and they get 10% of those changes as updates. That's a lot of changes. Their business should have made changes to make that not necessary, but this design will work with that kind of numbers. And finally, there's the use case that we're actually put into Hive 13, which required a lot of the framework, but it's if you want to hook Flume or Storm to stream data into Hive, there's now an adapter for Flume that will put your data into Hive and commit the transactions as it goes. So you can get much lower latency from the data. OK, so looking further out, what other things can you do further on? We'd like to get multiple statement transactions. You'd like to say, OK, I need to run this batch of commands, and they all need to succeed or all fail, right? No tries, just do or do not do. You also would like to be able to query the data as it appeared in the past. You'd like to say, show me the results of this query across multiple tables as it would have looked like last January. You should totally be able to do that. And finally, you'd like to be able to ask, who updated this row last? What were the previous values? What queries were they running, and when did they do it? So you can get auditing of who's made changes to your database. OK, now we're still storing the data in HDFS. HDFS doesn't allow you to write into the middle of files. You can add to the end, you can write new files, but you can't change the files that are already there. So what we're doing is we're storing the data as a base file and a set of delta files. Then when the client reads, he stitches them together into one coherent view. Each write operation, if you do an update or an insert or a delete, gets a transaction ID, and all the changes will be associated with that transaction ID. And if that transaction ID commits, then you'll read those data. If it doesn't commit, you'll just ignore them. Reads, on the other hand, get the list of committed transaction IDs, and that's all the data they'll see, regardless of how many jobs they run. Now, this is important. This is per query, not per a MapReduce job. So if you've got a multiple stage pipeline, you're going to get the valid transactions at the beginning, and each stage will see exactly the same data as the stage before it. That's important, right? That's the consistency part. So that kind of isolation is called snapshot isolation. And one of the features of this design is that the readers never block. It doesn't matter who's updating the data. You're always going to be able to read the values from when you started, and you won't get blocked. So what does the stitching together look like on the reader side? So you've got your base data. Then you've got your updates, which have insert, update, and delete rows. And you can have multiple updates. And the reader does a merge sort on these and will take the latest version of each row. Obviously, it's a delete. He just doesn't give anything back. But that means that you can easily go through efficiently, right? You don't have to store these things in memory. You're just streaming through these different files and stitching them together. The nice part about this is that you can get very, very high throughput on this approach. So what does the HDFS layout look like? The partition layout looks the same. You've got warehouse, you've got the database directory, you've got the table directory, and then the partition. Obviously, if you don't have partitions, then the level doesn't exist in this structure. The bucket files are structured by transaction IDs. The transaction IDs are sequentially increasing, and the base files are in the partition directory, but under base and then the transaction ID. That transaction ID is the transaction ID, the last transaction ID that's included in that base. Now, why do I have transaction there instead of just a single base? It's because when we do compaction, we need to leave the old version and the new version both there so that we don't kill the readers when we delete the old one. Okay, so again, you're providing isolation here. The Delta files have the partition directory and then Delta start transaction, end transaction. So again, we're going to be doing compactions and we want to have these side by side and know which transaction IDs are included in this Delta. We have minor compactions that merge multiple deltas together. Those happen, well actually, Alan will talk about this later, but they happen when we have enough deltas that we want to put them together, and it'll write them as a bigger delta, and that's when you get those two transaction IDs as different numbers. One of the important pieces, of course, is that compaction doesn't disturb the readers at all. Okay, so how did we actually do this? The first thing is that we created some new interfaces for Hive. We created the ACID input format and ACID output format. Now, users don't need to worry about this, right? This is just something that we used to make it so that it was generic with regard to which format you were storing things as. And they provide us the new methods that we need. The reader by default gives you the latest update, of course. We added a raw API. The raw API gives you all the events for the compactor, so you can see everything. And then we added to the ORC input and output format support for the new API. So out of the box, only ORC will support this. But of course, if the Parquet guys want to go through and implement it for the Parquet format, they can. Okay. Now I'm going to hand it over to Alan.
Thank you. All right, so one of the things you need to make this happen is you need a transaction manager. At the core of most databases, there is code that handles transaction management. So Hive already had some lock managers. Your lock manager and your transaction manager need to be integrated for reasons I'll talk about in a second. But so we already have, Hive already had an in-memory lock manager. Obviously, that's not durable if your server dies, right? So that was kind of just for more for testing. There's also the Zookeeper one. The problem with that is it adds another component into your system to administer. A lot of our users don't necessarily run Zookeeper. We just didn't want to put that in as a burden, like why make you add this new piece? Because it sort of turns out we have this database lying around called the Metastore, and we could sort of store lock and transaction information in there, so that's what we did. So as I said, your lock manager and your transaction manager need to be integrated because it needs to be atomic that when you commit or rollback that your locks are released at that same time, right? So these are two pieces of code that have to work well together. So we made that change so that both of these can now be stored in the database, or in the Metastore. Created a new interface called Hive Transaction Manager, which by default, if you don't turn this on, you get what's called the dummy transaction manager, which does nothing. You have no transactions. If you do turn this on, then it stores them in the Metastore. And we use the Metastore to provide unique ascending IDs for both transactions and locks so that you can tell going forward. This is also convenient because we can't use, since you're in a Hadoop cluster, you may or may not have time daemons running. We don't necessarily have a unique notion of time, right? So using the Metastore also gives us a consistent place to assign these IDs. So what is our transaction and isolation models? In Hive 13, which has some of this initial functionality in it, and I'll talk more about later exactly what is and isn't in there, we don't have explicit transactions at all. This is all we have is in here is the streaming ingest so far, which can do things in transactions, but there's no ability to say begin or commit or anything like that except in the interface that does the ingestion. When we do the implementation of insert, update, and delete, which we're working on now, the initial commit of that, when we initially add that feature to the code, it will be all auto commit. So that means as soon as you do an update or a delete or whatever, it just commits. There's no ability for you to decide when that commit happens. But we will come along after that and add, begin, commit, and rollback to these so that you can do cross-query transactions. It's a little bit harder to do those, to add the begin, commit, and rollback because I have to actually go write a deadlock detector into the lock manager, which I haven't gotten around to doing yet. So that's why it comes after the other stuff. As Owen mentioned, initially we have snapshot isolation. So traditionally databases offer dirty read, committed read, read committed, consistent read, and serializable as their isolation levels. So for the moment, we are only offering snapshot isolation. In the future, depending on what people want, we might extend that. There's nothing in this model that prevents us from doing any of those other isolation levels. It's not clear to us that people want that, so it's kind of a, what do people ask for? Serializable would be very painful in the way we've done things, but in our experience, nobody uses that as an isolation level in a data warehouse anyway. I'm sure someone will show up and prove me wrong, but, and from an administrative viewpoint, we also added this show transactions to Hive's SQL so that admins or even users can just go in there and see what transactions are currently in the system. There's already a show locks command, which is also integrated with this, so you can see what locks your query is acquiring. So let's talk a little bit about the locking. This was a fun lock manager to write, actually, because it uses, I've never had a three-way locking system before. This is kind of unique. So generally, in most lock systems I've worked on, you end up with shared and exclusive locks. But it turns out we actually need three types: shared, what I call semi-shared, and exclusive. So the semi-shared there is a semi-shared lock can share with any shared lock, but it can't share with a semi-shared. Right? So you can have at most one semi-shared lock, but still have any number of shared locks. Why is it we need that? So if you look at what the different operations need here, it'll start to make sense. Select and insert can both be shared locks. The first thought might be insert doesn't seem like it should have a shared lock. That's usually for read-only operations. But since we have no constraints in Hive, there are no unique constraints, no primary keys, it's never wrong to insert a row. When somebody does an insert, I never have to check that that row violates some constraint or whatever, so I can always allow inserts to occur concurrently. So it can be a shared lock. Update and delete are semi-shared, so those are the ones where on any given partition, we can support doing one update or one delete at a time. Reads can, as Owen said, reads can still go ahead while that's happening. That's not a problem because of the way our model works. The reader knows to strain out any rows that have transactions that weren't committed when it started the read, so it will just ignore anything written by those updates or deletes, or for that matter, inserts that haven't committed yet. And then obviously certain operations still require an exclusive lock, a drop, something, if you're going to drop the partition, that's an exclusive lock. We don't want you dropping the partition out from under a reader. Okay, so let's talk a little bit about the compactor. This is kind of one of the more interesting behind the scenes part of all this. So you write these Delta files. In the way we've done it, at least initially, each transaction, or in the streaming ingest case, each batch of transactions creates a new Delta file. As everybody knows, you get too many files in HDFS, your name node gets unhappy, bad things happen. So we can't leave it that way. And even if we could, even if HDFS could support infinite number of files, you don't want that, right? Because the reader has to merge on read, and you get the merge there too wide, and it's just going to get inefficient to read. So that's one of the things you have to do is build something behind the scenes that does this compaction. So we have two types of compaction, minor and major. Minor is where it goes along and collects all the existing Delta files and writes them into one Delta file, so you still have base and Delta. And then a major compaction is when you actually take the Delta files and rewrite them into the base so that at the end of that you have one base file. So what's that look like? This is minor compaction. You see here a base file, and then a series of deltas after that. When minor compaction is all done, you end up with one base file, one delta. And notice how the transaction IDs change. So the base file here you'll see doesn't change at all through this, but all these delta files get pulled into one with the transaction IDs there. At the moment, this is run automatically in the background whenever there's 10 or more Delta files. I had somebody ask me the other day, what test did you do and how'd you figure out 10's the right number? And the answer is, I sat there at my desk and went, 10 seems like a good number. So This is something we'll be working through as we, as we get more testing out there. That default may change, but it's configurable. So if you're using it and you find 10 doesn't happen to be a good number for you, it's easy to change. Major compaction looks similar, except that at the end of this base and all these deltas, now you have a new base file with a new transaction ID here that you see, and all the deltas are gone. So who actually runs this compactor? Right now it exists as a series of threads inside the Thrift Metastore service. So you get, this schedules automatically when these compactions are done. That means you as a user don't need to keep track of this. What it actually does is watch the transactions going by, and there's a thread that wakes up every few minutes and looks at all those transactions and says, I notice there's a lot of transactions on this table over here. I should go check and see if I need to compact it. It applies the rule of, are there 10 or more deltas? Or I guess I didn't say on the base, but on the base file, if it's the delta is 10% of the size of the base, then we do a compaction, a major compaction. It sees if those criteria are met. If so, it schedules a compaction. Then a worker thread picks that up and goes and does it in the background. So it runs a MapReduce job in the background to actually do that compaction. Again, this is going on while other inserts are happening, while reads are happening. All that's fine. When it's all done, it puts it hands it off to a thread called the cleaner thread, whose job is to wait till nobody's reading the old files and then remove the old files. So all this can go on with no pauses, no requirements, no requirement to disrupt current readers or writers. And we've also added a show compactions piece to the language so that you as a user can go and see what compactions are out there. And also, if you do, for some reason, want to force a compaction on your table, we added an alter table compact statement so that you can force a compaction if you have some desire to do that. But again, you shouldn't need to. So I wanted to talk quickly about an application we built with this that I hope will be one of the kind of first big use cases. I think it's very interesting, which is streaming ingest of data. So if you think about a very common use case in Hadoop is you have something, and I'll use Flume as an example here. Flume is the first thing we've integrated with this. You have something like Flume streaming data constantly into HDFS. It's very good at that. It can drop records, hundreds or even thousands of records a second. That all works. But before Hive 13, the only way to get that into Hive was to wait for some amount of time, 15 minutes every hour, and add a new partition. But what that means is your data is sitting there on HDFS, but your users can't see it unless they're using Hive. If they're using Hive, which is pretty bogus. We're adding this latency there that's not needed. So the goal here, what we've done is add a new interface called Hive HCatalog, in the package Hive HCatalog Streaming, where things like Flume can connect to this. They can write their batch of files, say, maybe they drop a batch every 1 second, or maybe every time they get 10,000 records, whatever configuration they want to do, that's up to the stream writer. And each time it writes that, what it's actually doing is appending to a file in HDFS and sending a commit to the Metastore so that readers can now see that. So that means that your Hive users can now see this data within seconds of it arriving on HDFS instead of within minutes or hours. Right? So let's have a quick and sorry artistic example of how this works. You'll quickly see that I have a math degree and not an art degree, and why I would starve if I was in art. But so let's say you have a Flume agent here. It's writing data to HDFS. What this would look like is it's got some while loop here where it writes and writes and writes, and then it calls commit on that streaming interface. The commit underneath actually does a flush to HDFS to make sure it's on disk, and it also sends a commit message to the Metastore so that the Metastore knows that this is now good data. For the next pass, it's going to do the same thing. It, again, writes a bunch, commits. Observe that this is being appended to the same file, so it's not creating a new tiny file every second. That would be a bit much. At the same time, it continues to write. You can have a reader that comes in. It is told by the Metastore what transactions are and aren't valid. So he can read from those first 2 blocks that are, have been committed. He'll actually read through the 3rd block and just realize, okay, all the transactions in here are not yet valid, so I will simply ignore them. All right, so where are we at on this? What are our the phases? You know, Rome wasn't built in a day, and neither will Hive on Acid be. So phase 1, Hive 13, which has been released. The transaction manager and lock manager are included in there. The org file changes that Owen talked about are available. Automatic and manual compaction is in there, as I talked about, the snapshot isolation, and the streaming ingest via Flume. We haven't yet integrated this with Storm or any other systems, but we at Hortonworks want to do the work to get it in Storm. It's in our plans. It would be easy enough to integrate this to any other, you know, whatever your favorite streaming solution is. Phase 2, which I'm hopeful we'll get in Hive 14, but we'll see, is to add insert values, update, and delete. So this would mean to the language, you would actually be able to say insert values and give some constants. You would kind of think at a first pass that might not actually be that important for a data warehouse, but it turns out a lot of BI tools like to be able to do that for temporary tables and that kind of stuff, so we'll support that. For reasons that Owen talked about before, update and delete are very useful for restating data or for you know, anything like that. So what will we do at some point in the future? Owen kind of talked about this, but I'll cover it again a little bit. Versioned or point-in-time queries. So it's funny, we didn't start out thinking this would be this big a deal, but the first, I don't know, 5 to 10 people that we showed this to, I think every one of them said, oh, if you could do that, could you like make it so that you can, you know, if I do a query in the morning and in the afternoon, I can go back and do the query again? And the answer is, yeah, we can. Because we're keeping those transaction IDs in there, we could snapshot a query. We could snapshot the state of the transactions at a point, and then if you could somehow give us back that transaction, or sorry, that snapshot, we could recreate that. Now there's a couple challenges. One is, how do you do that nicely in the language? SQL doesn't give you a way to do that naturally. So we need to figure out how do we integrate that nicely with the semantics. The other is, we have to not run the compactor in that time, right? Or at least not the major compactor. Minor compactions don't get rid of deleted rows, but at a major compaction, we truly dump rows that we don't need, and we dump updated, you know, earlier versions of rows that were updated. So if you were going to version this, we would have to say, okay, don't change those. But that also brings in the question of how long back do you want to go with these versions? Because now you're making a time-space, or a functionality space trade-off. The more versions of the records you keep, the farther you can go back in time, but the more disk you're burning up. So you have to decide what you want to do. So we have to figure out how to make that all usable in a nice way. As I said, we could add additional isolation levels at some point in the future. We could also add merge functionality, SQL merge functionality, if people were interested in that. So limitations. This is important. We should have probably put this in the first big slide in like flashing, you know, lights or something. We are not trying to be OLTP here. We are not trying to kill Hbase, and I'll talk in a minute about Hbase. But that's not our goal. This is not, if you try to hook this up to some system that's going to do hundreds or thousands of transactions a second, it will fall over. And when you call us and say, hey, it doesn't work, we'll say, yeah, you're right. It doesn't work for that. So that's not what we're going after. But data warehousing you know, for reasons we've already covered, data warehousing needs transactions too. But we just want to be really clear that we don't see this as an OLTP solution. Tables must be bucketed. That's just so that we can search quickly inside those buckets when it's time to do the merge on read in order to quickly find the records. For, you know, when a row has been updated or deleted, we want to do that join in an efficient manner. And currently, we don't support sorting inside the table. Hive allows you to pre-sort buckets so that you can do merge joins. That's not supported at the moment. That's something we can remove in the future. It was just easier to implement it in the first pass without supporting that. All right, so why not Hbase? This is usually the first or second question people ask, like, why didn't you just use Hbase? So Hbase is good in that it handles the compaction for us. Hbase already does these compactions. It already has a similar data model with its LSMs where it keeps changed data in memory and it keeps versions on disk of what it's written out. But it's one of those funny cases where the first time you look at it, and the first 3 times I looked at this, I thought Hbase was the right solution. But after you look at it longer and harder, you realize it's not. It's actually a wrong solution and a really wrong solution. Why is that? Hbase doesn't give you cross-row transactions. In order to get that, you would have to write a transaction manager over the top of Hbase. Now, we know how to do that. Google showed us the way in one of their papers.
Was it Percolator?
Yeah, thank you, the Percolator paper. So you can do that. It's not trivial. It was a lot of work, and in fact, looked like it was at least the same order of magnitude of work of what we've done, if not more. The H-file format that Hbase uses is column family based rather than columnar. With a lot of the new work Hive's doing, it's very focused on being a columnar store, so that didn't look like a good fit. And finally, Hbase is focused on doing point lookups and range scans. It's excellent at that. Hive, doing data warehousing queries, almost every data warehousing query or analytics query ends up scanning large points of data. That's not what Hbase is super good at. Some people have tried to get around that by integrating these to having Hbase Snapshot so that you can do a scan, so that you would then merge the Hbase Snapshot scan with your base data. But then you've got, I don't think that's going to perform super well if every time you want to do a read, you have to force a snapshot on Hbase.
Well, and you've got latency issues also.
Yes, so it just didn't work out as a great solution there. All right, so kind of in summary, here's the JIRA that 5317 that we're doing the work under. All the sub pieces of it are connected to this. A little pitch here. At the moment, this is the most watched JIRA in the Hadoop ecosystem, and we'd like to keep our lead in that battle. So please, if you're interested in this, go watch this JIRA. Just help us keep our bragging rights over some of the other teams. All right, I think we covered all the rest of that. So with that, questions? Yes? So the question is, considering that we're keeping base and delta files on the same server, are we getting a huge network hit when we do the same scan?
Basically, no. Of course, it does cost you some overhead, but the delta files are typically much smaller than the base files, and so there's some overhead, but it's not outrageous. It's actually relatively small. Let's see. Well, back to my favorite customer. They're getting about 3 terabytes a day of data, 10% of its updates, and the updates go spread out over 10 years.
But remember, as soon as the delta file size reaches some configurable amount, at the moment set to 10%, we do the compaction. So, and if you were concerned about that issue, you could dial down the amount that you waited till then, right? Other questions? I think we had one right here. So how do we clean up the metastore? We forget the transactions after they're committed. So what we reference that the reader's given a list of transactions. That's not actually true. What the reader's given is a high watermark and a list of transactions below that watermark that are either open or aborted. At major compaction, we clean the aborted transactions because we know we've rewritten and we no longer have to remember them, right? So what we're actually keeping is, a fairly small record. We don't track every transaction. Now, some of those other features people wanted, like lineage, it might become useful to actually keep every transaction, in which case we'd probably write it in a log on each DFS or something, because otherwise, you're right, the metastore would overflow in a few days without that. Other questions, yeah?
You'd almost certainly want it to be on a table-by-table basis. Ironically, the only place that needs to change is the major compactions. And so yeah, if each table had a parameter that's like how much history to store, then it would be doable.
Yeah. Go ahead. Okay, so the question is, how do the delta files affect the cost model? So in any database system, you tend to take stats every once in a while and live with the fact that that it's a little bit off, right? So the delta files would not be calculated into the cost model at this, and I doubt that's going to be much of a problem. When the base files are recalculated, if you're using ORC, which at the moment you don't have any choice, it actually stores enough statistics in the base file, which would be created on rewrite of the base file, so you would get that for free. If you were using something else, you could do an analyze table after a compaction happened if you wanted. But I mean, the general approach to those, if you're not going to auto-collect stats, is to manually collect them every once in a while when you figure things get too far out of a drift, which is the same thing we would do here.
Yeah, clearly major compactions are a great time to recalculate stats.
Yes. Yeah, in the back.
No,
not
actually
quite.
they aren't.
Not quite. So they have different transaction IDs. So if you see...
So the delta files have a begin and end transaction ID?
Yeah, so see here how you go from 2801 to 2805 here. So now this file contains everything those files contained. Yeah, okay.
Yeah.
So that's why they have a begin and end, yeah, to avoid exactly that problem. Yes? Oh, sorry.
It's okay. Concurrency problems here.
Yeah, we need a lock manager. Sorry, go ahead. I didn't hear you. Yes, so
Yeah.
we will. So will we do multi-table transactions? Yes, when we do begin commit rollback, we will. That will do the multi-table. That's why I have to write a deadlock manager or deadlock detector before we can put that in, because otherwise you ask for you get A and then ask for B, I get B and then ask for A, and we're wedged, right?
And actually, even the reads right now are multi-table transactions, right? When you get a snapshot, you get a snapshot for the whole database.
Yeah, that's correct. I think you had a question.
Yeah, my question is how indexing fits into this picture?
How does indexing fit into this picture? So we don't do any auto index update at this point. That would be something you would have to go behind and rebuild. Anything else? Oh, sorry, there's, go ahead. But there's one over here afterwards, but go ahead first.
Go ahead.
If all the help jobs will support ACID features, will overall performance upgrade or degrade?
Will the performance degrade because of the, so you're going to see a little cost on read, right? Because you've got to merge. But I don't think it's going to be, I mean, I don't know if we've done a ton of testing.
Yeah, we
yet,
haven't done a bunch of testing, but on the other hand, the customer that's doing it sees somewhere between like 2 to 4% degrade. It depends a lot on how many deltas you're merging, to be honest. It's most sensitive to the number of deltas.
Okay, I think we had one over here. So the question is, on minor compaction, do we sort the deltas as they're coming together on the assumption that it'll then make, well, one, it could make the merge more efficient, and two, it could make the final major compaction more efficient? The answer is no, not at the moment. We don't. We just put them together, and that's it. We could look at that.
No, actually, sorry, it actually does it does actually do the merge sort on minor
okay, so it merges them by
so
transaction ID. Does it?
Yeah.
Oh, you must do that underneath, because my
Yeah, I
stuff
do.
doesn't do that.
My stuff does that.
Okay.
So yes, it does do the merge sort on the minor compactions, because you want to be able to stream through the base file and the delta files one way without having to jump around. So yeah, everything is merge sorted when you do a minor compaction or a major compaction.
Yeah, it doesn't resort the base.
It doesn't resort the base. It just makes sure that the delta files that get, the delta file that's being written is sorted the same way that the base file is sorted.
Okay, one more question, and then I think we got the sound guys want to go home, so. Yeah. What's that? Yeah, it works fine with external tables. Internal, external doesn't matter. All right, thank you very much.